So this is experiment number 3, the simple distillation and refractive index of n-Hexane, so normal hexane, straight chain hexane, and toluene. This is a simple distillation such that we do not have to use a column in order to maximize separation of the two liquids, that is to say the purity of the two. And we can use simple distillation because they've got a difference in boiling point greater than 40 degrees Celsius, which is generally thought to be a good rule of thumb in terms of deciding whether or not you should use simple or fractional distillation. If it's less than 40 degrees, for example, if you had a difference in boiling point of only 20, then you would use fractional distillation. But today we're using simple distillation because the differences in boiling point are about 42 degrees. The boiling point of normal hexane is 69 degrees, and the boiling point of toluene is 111 degrees. We are going to perform this simple distillation at atmospheric pressure, and after we collect our 3 fractions, we will analyze the purity of each fraction by using an Abbe refractometer, and with some simple arithmetic, we'll be able to tell ourselves how well we achieved separation and how pure fractions 1 and 3 are. So we'll talk about the refractive index a little bit later, but basically the two liquids have different refractive indices, and there's a substantial difference, which is why we've chosen toluene and hexane as the two solvents to distill from each other. That and because of their great difference in boiling point. So what we need today is we've set our Corning stirrer hot bath to about 4 to 5. We've got our porcelain crucible about halfway filled up with sand. And for the distillation, we're going to use the same Hickman-Hinkle distillations still head as we did for steam distillation. And at the top now, rather than having an air condenser, this is called a Claisen adapter. A Claisen adapter. It looks similar to a saguaro cactus, like this is one of its branches coming out to the right. But the one that's going straight up and down is where we're going to put our digital thermometer, the probe of a digital thermometer down right in here in order to determine the boiling point ranges of each fraction, fractions 1 through 3. The sidearm of the Claisen adapter will be left open to the atmosphere because, of course, we would never want to heat a sealed system. Otherwise, you could be making an explosion for yourself. So other than that, what we've got are 2 different automatic pipettes, and we've got hexane, normal hexane pure, so only 1 isomer of hexane, the straight chain hexane, this is why it's called normal, and then we've got toluene. These are very high grade solvents from TCI, and we're going to distill 1 milliliter of each. So we're going to combine 1 milliliter of hexane with 1 milliliter of toluene into this 5 milliliter reaction vial. So this is the reaction vial. You can see it's heavy walled glass here. This one has a flat bottom surface, so it can stand straight up on itself, rather than a conical vial, which cannot, and of course the round bottom flask cannot. This reaction vial is heavy walled and can sit up and down straight. So obviously, since we're going to be adding around 2 milliliters total, our volume is going to be around that. But before we add the liquid, we want to add our Teflon coated magnetic spin vane. This is our spin vane, and we want the point or the apex to be pointing down so that it's in the, it'll properly spin in our reaction reaction vial. All right, so just like that. And you can always test to see if it'll spin properly. So I'm changing the stir setting now, and you can see that yes, we've got spinning. And we'll talk about a little later how Teflon expands upon heating, so it might be an issue later if the Teflon magnetic spin vane chokes or stops stirring. If you're to look at the stir hot plate and peer through the edge down here, you can actually see the rotor spinning around. So it's spinning a magnet, which is why the spin vane itself is actually also stirring. Okay, so let's hope that this goes well. So I've got my spin vane in my 5 milliliter reaction vial, and now I'm going to combine our two liquids. So I want to be sure that I'm using different pipette tips, or that's to say different automatic pipettes. And the first thing you want to be sure of is that you're actually going to add 1 milliliter. So you check on the depressor here, and it goes from 100 to 1,000 microliters. So 1,000 microliters is 1 milliliter. So that's the maximum of this automatic pipette. So, and then how to change that is then you look at the side, and here's a dial right over here on how to change the volume that the automatic pipette will draw up. So right now, it's set to 400 microliters. And I'm going to keep climbing, obviously, because I want to get to 1,000 microliters. And it will say 100, and it's going to be red because that's the maximum capacity of this particular pipette. All right, so 100, I'm trying to get the line just so where this is pointing to. And so this is now 1,000 microliters, aka or equivalent to 1 milliliter. All right, so this one on the right we'll reserve for hexane, and then we'll do the same thing with another pipette for toluene. Okay, all right, so these automatic pipettes, the depressor here has 2 levels of resistance. So there's this one here, which is easy to do, and then now my thumb is applying more pressure, and that's the second level of resistance of the depressor, or you could also call it a plunger, right? So when we're going down to this level, this is where we're going to then draw up the liquid, and we want to do it slowly to avoid grabbing it too quickly and capturing perhaps some air or just some vapors of whatever we're doing. And then the second level is how we're actually going to deliver the rest of the liquid. All right, so it's pretty straightforward. It's something that you might use later on, especially if you're going to take the second semester component of organic chemistry lab, or in your future career. So these are very popular to use, and it's good to know how to calibrate them and to be sure that you're actually adding the proper amount of some liquid. All right, so here's hexane, boiling point 69 degrees. It is a clear, colorless liquid. Also, we call that a water white liquid. It doesn't really have an odor. It's just sort of an industrial odor. And so now here, if you look at my pipette tip, this is what is 1 milliliter, right? And so this is what I'm going to deliver, and then the second level of resistance just gets everything out. So once again, I'm going to very slowly draw up the hexane and now deliver it to my 5 milliliter reaction vial. And then now the second organic solvent, toluene, which is also a water white liquid, which has a distinct odor. is the other 1 milliliter now added of toluene. So we've got 2 milliliters of liquid in there now. Obviously the vial takes up some volume, so it's higher than the mark, the graduation there for 2 milliliters, but now we're all set to go. So I'm going to take my reaction vial, and I'm sure that I want to be sure that there's this O-ring here to create a nice seal. This is the male joint of the Hickman-Hinkle still head, and now I'm going to fix it to the reaction vial, and then I'm going to use this screw cap to be sure that there's a nice seal, just like that. All right, and you can already see even from this height, as it's hovering, and I'm going to try and get it centered perfectly over the stir hot plate, the magnetic spin vane has already begun to stir. So now I'm going to use my digital thermometer. It's important to note perhaps that it's 22.1 degrees Celsius in here today, so it's not the nicest temperature to work in, but I'm now going to replace that with my digital thermometer, and I want the probe to be in the throat here to get an accurate reading of the temperature of the distillate that we're collecting, right? So I want to know the vapors, the temperature of the vapors that we're collecting, so that we can report a boiling point range for each of the fractions that we collect. And the first liquid that will boil and then in its vapor form condense on the cooled glassware here should be, of course, the lower boiling solvent, hexane. And then as the hexane distills out, we'll see that the temperature will drop somewhat because there's no more hexane left to distill. So that should be our first fraction, and then we'll separate it into this little sample vial. We're going to collect our distillate just like we did in steam distillation through the sidearm of my Hickman-Hinkle still head. And so that should be, if we're good at this, the hexane should be pure. And then fraction 2 is going to be that in-between period. So when hexane is done distilling and when toluene is starting to distill. So obviously this will have to get warmer. We're going to increase our temperature here, and we might even use some aluminum foil to help vent, to help insulate our setup because it's much higher boiling. All right, so now I'm going to be sure everything's centered, perpendicular to the lab bench. There's something wrong with this here. It might be the screw cap. Oh, there we go. All right, so plunging into the sand here, and so now we're on our way to glory. And what we can do is use a little spatula. Let me grab one. To help push some of the sand and try and maximize the amount of heat being transferred to our reaction vial. And so we're going to collect distillate out of here. We're going to be able to see that once the hexane starts boiling, we'll see it start to vaporize, condense down until back and forth, back and forth, back and forth until the glassware is the same temperature as the boiling point of hexane, and then we'll be able to start collecting our first fraction. We're going to collect our first fraction, well, actually all fractions, with Pasteur pipettes, and we're going to use 3 different ones, of course, to try and minimize contamination. Okay, so after waiting about 4 minutes, we see that in the reaction vial, something is boiling. And of course, that's going to be the lower boiling component, the normal hexane. And our spin vane is spinning very nicely. And what we're hoping for is that eventually the vapors are going to travel upward, reach the probe, so we'll know the temperature of the vapors, the distillate, and then collect it in the well of the Hickman-Hinkle stillhead. And so right now it just started boiling, so there are no vapors yet to hit the thermometer, but we can see that the air in there is hotter just because of the fact that it's over this hot plate. So it's 30.5 degrees now, but we're going to expect close to around 69 once the vapors of the hexane start to rise. Okay, so now we can definitely and clearly see that the vapors of hexane are climbing the walls of the glass, so to speak. So the vapors are condensing on the glass and heating the glass up at the same time. So once it's established in equilibrium, that is to say that the glass is the same boiling point of the vapors themselves, then it'll no longer condense here. And in other words, it will continue to climb upwards. So right now we're just waiting for this part of the glassware to be the same temperature, around the same temperature anyhow of the vapors, so that it won't keep refluxing in this arena. And we can already start to see now at the juncture between the 5 milliliter reaction vial and then the Hickman-Hinkle stillhead. If we peer down in here, well, we might be able to start seeing that those vapors are doing exactly that in there. But once again, so our thermometer probe right here, right down in the throat of the stillhead, once the vapors climb to that region, it will then start condensing on the probe itself, and that's when we're going to start measuring. We'll be able to tell the boiling point of the vapors, and then finally, once it starts to reach the well of the stillhead, that's when we're going to start recording the range of our boiling point. Okay, so it's still taking some time, and what we're doing is that once this is collecting here, our first fraction, we'll take off the screw cap, use a pasture pipette, try and angle it so that we don't break the glass, and then we're going to add it to sample vial fraction number 1. And in the notebook, we've already started writing down the boiling point ranges to fill in for each of these fractions. All right, so the vapors now have finally traveled past the screw cap, and we can see that they've now started to condense on this portion of the glassware, and also look at that droplet on the very tip, the base of the thermometer probe. So if we're just elevator upstairs, we see that the temperature, of course, has increased. It's now 45 degrees and will continue to climb as the vapors make their way towards the well of our Hickman-Hinkle distillation hub. So we just have to be patient and continue to wait for this to come up. It's a very cold in this laboratory, so I'm actually going to use some foil to very gently insulate so that the air in the lab won't continue to cool the glass, and it'll actually continue to climb upwards. So we're just loosely insulating it with this aluminum foil. And we already see that it's doing a pretty effective job at that. So you see now it's climbing past it. The thermometer reads 70.3 degrees, which is fascinating. And here we see, okay, it's starting to reach the well. Once it starts spilling over, that's when we're going to record our temperature. All right, so here it's lifting, it's starting, so we're at 71.3 degrees. So we'll write that down in our notebook. And so obviously now we're just waiting for this liquid level to increase in volume, and we're going to monitor the temperature. So once we've got the maximum and then the temperature starts to decrease, then we know all of the hexanes has boiled or distilled off, right? Because our distillate should be 1 milliliter. And so we're still climbing. It's at 74 degrees right now. And of course, we see that the distillation pot or the distillation vessel, our 5 milliliter reaction flask, is boiling down there. And we're at 75 now. Look at that. You can see the vapors just really nicely climb over. Filling the well very slowly. 76.1. So now we're reaching the territory where it's going to start overflowing. So this is a good point to now collect the first fraction. So we're going to unscrew this. We're at 78.4 right now. And so remember, it's volatile, so I want this close by. And now that's fraction number 1. Of course, I'm going to seal it so that my vapors don't go anywhere. And then I've got to quickly put my screw cap back on to now start waiting for fraction number 2. And now I'm going to replace this pipette because I don't want contamination. And we're going to see obviously now that, so we stopped at 78.3 and now we're still climbing to 81.6. So while that's still distilling, if we look at our notebook here, fraction number 1, our boiling point ranges were 71.3 to 78.3. And then fraction 2 is then 78.4 to, and we're still climbing up to around 83.2. And we should hopefully try and gather what we can for the second fraction before there's too much volume in there. And so now what this is distilling over should be our toluene. So the second fraction is sort of, we can call it a wash fraction in the sense that the toluene is coming over now, and this is good. So 84.6, I'm going to now collect this fraction because the temperature is going down now. And so now this should be toluene that's come over, and when we collect that, we've sort of rinsed the arena of that well of any remaining hexanes. So now that was, what did I say, 84.6? Mm-hmm. Now what we're going to do is we're going to increase the heat to about 7 to 8. You can look down, of course, it's nice to always do that, and see that there's still liquid remaining, and so that's the remaining toluene, and so we'll stop once all of the toluene has distilled over. And so it's going to be 85.6, and we continue to note that the temperature is still rising here. All right, so now we're collecting fraction 3. We can see now once again that the distillate is coming over, so the vapors are condensing on the cooler area of the glassware and coming back down, or they're just sort of falling over at that little bevel point right there. And very clearly, it's pretty hot down there. Look at the toluene just boiling, sort of making its way past that thermometer pretty rapidly. Temperature right now is 105.5 degrees and going and climbing. And so we're just going to wait basically until all the toluene is almost gone, and then we'll turn off the heat because we don't want to just heat the vessel without any liquid down there. So 107.8 is still going. And so now you see that very clearly the toluene is condensing now from this side of the wall as well. It's much higher boiling than hexane. And the aluminum tent that's loosely insulating this is very necessary. .9, 110 is the thermometer. It should not go past 110.9, otherwise we've got a faulty thermometer. The boiling point of toluene has been 110.9 for years. But it's pretty cool to see the vapors of toluene have now reached this level and are falling down and collecting here. The well hopefully is not too shallow for it to then just fall back down in there, but we shall see. Because then we're just achieving a reflux rather than a distillation. Alright, so this is good enough. We don't need to distill to dryness. So this is going to be our fraction number 3. The maximum we saw was 110.1. And I, of course, have a new pasture pipette. Unscrewing the side arm of the still head. You can even see the vapors start to come out of the area. This fraction is much hotter, which makes sense. It's higher boiling solvent. And we are done. So we turn off the heat, get rid of the aluminum tent, and I'm going to lift the reaction flask, or the reaction vial out of there. So we pretty much did a good job at almost distilling all of the liquid in there. And so now we've got our 3 fractions here. Fraction 1 should be hopefully mostly hexane. Fraction 2 should be our wash, so a combination of the two. And then fraction 3 we're hoping to be just toluene. And now in order to assess our work, if we did a good job or not, we will use the refractometer and get the refractive index of each fraction. And the first thing we'll do is we'll get the refractive index of the two standard hexane and toluene. And so that will be a separate video next. Okay, so this is our refractometer. What we have here is where we're going to put the sample. And what this is it's a prism that will have the sodium D light shine through our liquid, which is 589 nanometers, which is the wavelength that has been chosen historically to measure the refractive index. And so 589 nanometer wavelength of light is going to pass through the liquid from this lens, this light here, pass through the prism, and then that's the light that's going to go through it. And so the theory is that when the light passes through the liquid, it's going to be refracted somewhat. So that is to say, bent. And the picture in the book sort of illustrates that. So this is where the the light is coming in, and then it's going to hit the small layer of our standard and then our fractions, and then it's going to be bent somewhat. It's going to refract as it travels through this. And so from there we'll be able to determine the extent at which that occurs, and we get a unitless number n for refractive index, subscript capital D for 589 nanometers, the sodium D line. All right, so I've got my sample area. This is going to be collecting our the standard of hexane. And so now this is the sample area. Note that I'm using a plastic pipette because I don't want to scratch it with glass. And then I'm setting it down, and now we're ready to read the refractometer, as long as we can. There we go. All right, so the crosshairs, I'm turning a dial, which I'll show you later. So that's what I want to see. And I want the horizon here to cut directly through there and meet exactly where that X is. So now that's exactly where the refractive index is. And there's another button that we, not a button, but a little pin where we push it downward, and then we get the exact number of the refractive index. And so this is a vernier scale, and if you look at it, we've got 4 significant digits to work with. 5. And so we've got 1.370 going into 1.380. So the 1.375 is right in the middle, and then the medium-sized notches, 1.376, 7, and 8. So where that line is 1.378, and it's directly in between 1.378 0 and 1.3785. And so what we can say is that it's 1.3783. So that's our last digit of uncertainty, that number 3, but that's what we're going to go with. So 1.3783. So we used a manual refractometer. Now they, of course, also make digital ones. So this is an Atego RX 5000i. If you look at the LCD screen here, we've got a bunch of nice data to look at. So today is the 13th of August, 2020. And it also tells us the current temperature, which is 20 degrees. That's ambient temperature or room temperature. Okay, so I've got my hexane, the same that we used, and I'm going to put a little bit in its lens area, which is right there. Cap it, press start, and then it does it for you. So it says it's reading, and it also gives a nice little chime. So this one says it's 1.37 959. So this is 6 significant figures. So perhaps we can take an average between the two, or you know, if we're working with one instrument and that fraction, you use this as the standard number. Okay. So that was hexane, and next we are going to take the refractive index of toluene. So I'm using these Kim wipes. They're delicate task wipers, I guess would be the generic term. And so it's nice because these do not scratch glass or quartz. So we would use these on this type of instrument. We use the same thing on our infrared spectrophotometer. So I'm cleaning off the hexane, letting it air dry while I walk over and go get the toluene. And I'm going to use a new plastic graduated pipette, toluene, pure, standard, a couple drops there. Press start. And that magic sound gave us 1.49671. And as I'm writing this down, I realized that I put the numbers on the wrong area of the notebook. So if you make a mistake, you just cross it out. So this is actually n-Hexane, and this one over here now is toluene. So this was with the digital one, and now we're going to take it again with our analog version of the older Abe refractometer. So it's still on over here. And by the way, this was the knob that I chose to first turn on the instrument, so to have the light on it. And then once you have the light, you see those crosshairs. If you depress it once more, you then get that vernier scale to go ahead and actually read the refractive index. On the other side of the instrument is this dial that I used to try and get that dark level, give us a half moon, and hit that crosshairs exactly. So I've left this open to the atmosphere so that all the hexanes now should be gone. And now we're going to measure the same bottle of toluene, but with this refractometer. They're adjacent to one another, so the temperature should be the same. Close, and then bring the light up to the prism. And now we should get close to 1.49 as the digital one indicated. So there we go. And there's another fine tuner that is in the front that sort of helps, so that's this one here, let me grab it, that is going to help sharpen that line. So we're back in there. It's very hard to get this. But I'm adjusting it now, and you can see that horizon is getting flatter. Yeah, perfect. So fine-tuning it there. It's pretty good. And then I'm going to go up to the crosshairs, get it set. We then depress that little knob on the side. We then get the vernier scale. We see that the line is almost dissecting, it's dissecting very closely to 1.495, but it's close to the second medium-sized notch, which would be 1.496. So in between that is 1.4955, but it's just slightly shy of that smaller line between 1.495 and 1.496. So we're going to say that this is 1.4954. 1.4954. 1.4954. Okay, cool. Okay, so we're ready to take the refractive index of fraction 1, and so this should be close to the value of hexane that we measured earlier. So I'm take a little bit. Don't want to take too much because I also need some for the digital refractometer. So first fraction, and now we're going to look down the eyepiece. And there we are. I'm going to fine tune it just a little bit. All right, and then now we've got our vernier scale. So we've got it right at the half moon, and now this is, if we're looking at it, it's hard to, there we go, 1.39, 1, 2, 3, so 1.393, 1.3933. So that's this one, 1.3933. That's with the Abe refractometer. Now let's go over to the digital one, still fraction number 1. Much easier. .3953, which, what did we say was 1.3933. So with the digital, we've got 5 significant figures, 1.39530, and that's from the digital one. So we know that fraction 2, we're admitting ahead of time that fraction 2, also look at this sample file cap, just so you're aware, the hexanes has sort of dissolved the plastic and the snap cap isn't able to go on anymore. But good thing we've already got those. But normally we don't take the refractive index of fraction 2, but since we've got a decent amount, we're just going to do that, and then we'll still be able to prove to ourselves that it's a mixture. But that makes complete sense because we knew that fraction number 2 was a wash. So same procedure. just going to look down at myself. This is 1.440. 1.440. 1.440. All right, and then while we're here, might as well do fraction 3. Let the vapors go away. I'm wasting these chemicals. So now, of course, this should be closer to the refractive index of toluene. .4759. That's almost exactly on the spot. That's pretty cool. And so now those are the Abe readings. And now let's get the digital. Here, we'll start with fraction 3 since I already had it open. And we've got the same pipette. So we should see the value of toluene be the same for the digital one. .47843. And the value for toluene was 1.47671 according to the digital one. And now fraction number 2 with the digital refractometer. Fraction 2. .40504. So that means I must have read it wrong on here. Right? Again. Turning into a cemetery of chemicals. Last of it. 1.40 1.40 1.4040. So there we go. Now we got the right readings. All right, we're done. All right, so now we're going to use the refractive indices. We're going to use these data in order to calculate the percent composition of each fraction. And so we're assuming that the refractive index is a linear function of the volume fraction. And so this is the following relationship, which gives us the volume fraction of hexane in a mixture, where X is equal to the volume fraction of hexane and the measured refractive index. So if we go ahead and look at our numbers, right? So these were our standards. So for toluene, it was 1.4954 for the digital, and for the analog, and 1.49671 for the digital refractometer. And for normal hexane, our standards came out to be 1.3783 and 1.37959 analog and digital respectively. So for fraction 1, we can already tell that we got the ND, so the measured refractive index, closer to that of hexane, and then fraction 3, obviously in the opposite direction, closer to the standard refractive index of toluene. And then also fraction number 2, which seems sort of in the middle, which makes sense to us. So using that equation, we can just do some basic algebra here. So fraction number 1, the analog one, remember we measured to be 1.3933. That's what we measured for fraction 1's refractive index. And so X times the standard refractive index of hexane that we measured, plus 1 minus X, times the refractive index of the standard toluene that we measured, works out to be then 1.3783X plus 1.954 minus 1.4954X equal to the measured refractive index that we obtained. So then from there, we subtract 1.4954X from 1.3783X to give negative 0.1171X, and then of course 1.3933 minus 1.4954 gives negative 0.1021. So to solve for X, it's negative 0.1021 divided by negative 0.1171 to give you 0.8719. Multiply by 100 and you get a percentage, approximately 87% normal hexane and 13% toluene, right? So this is a decent separation for fraction 1. And the arithmetic worked out to be the same for the digital. We still got the same ratio, 87% hexane, 13% toluene. For fraction 2, this is fraction 2. It works out to be 78% hexane, 22% toluene, and that was the case for both the analog and the digital. Fraction 3, which we were more concerned about, we measured 1.4759. Our standard for toluene was 1.4954. So doing the arithmetic as mentioned above, it's still 0.1171x, and now this is set to equal to 1.4759 minus 1.4954, which is negative 0.0195. So you divide that by negative 0.1171, and you get x equals 0.1665. And there's another significant figure. Anyway, we rounding this up, multiplying by 100, and that gives 17% hexane and 83% toluene. And that's what we wanted to see. We were aiming for separation such that fraction 3 should be mostly the higher boiling solvent, toluene. So the distillation wasn't perfect, of course. We can see that in these data. Also something similar read out for the digital one. But nonetheless, the majority of fraction number 3 was the higher boiling toluene, 83% composition. And then the first fraction that came off was the lower boiling solvent, normal hexane, at 87% composition. So you should be able to understand these calculations, and then given some examples either on a quiz or a worksheet, be able to illustrate to your instructor that you are able to manipulate the equation and rationalize why these numbers worked out this way. Right? And once again, makes sense. Fraction 1 is comprised of mainly the lower boiling solvent, and the opposite case is true for fraction 3. It's comprised of mainly the higher boiling solvent. And that's all.